legen wir los. Das heißt, wir haben ein paar Minuten Zeit zum Entspannen. Genau, was machen wir denn heute überhaupt?
Also eine kurze Frage
Ja.
zur Übung.
Ja.
Dürfen wir Hashmaps benutzen? Oder
Meinetwegen.
es geht nur um den Elvis-Server, nicht zu den anderen.
Ja, da können Sie das machen.
Passt. Okay.
Da merkt man gleich, dass der Herr Schiata komplett auf Kotlin getrimmt ist. Das ist mit dem Elvis-Server, aber das ist ja der Environment-Server, aber das ist schon nah genug.
Ja, ich will es halt mit Callbacks machen, also die Routes und dann ein Callback dazu.
Mhm. Ja, spielen Sie ruhig ein bisschen rum, kann nicht schaden. So, zur Blick auf die Uhr, 42. 31 Nasen. Gibt es wieder irgendwie eine größere Gruppe, die im L2 rumsitzt oder so? Kein Feedback. Der Herr Fischer ist aber schon da. Sascha, bisschen umgenagelt. Auch nicht. Gut, wir warten bis 45 Maximum und dann. Oder bis wir 35 Personen sind. Morgen. Okay. Wie gesagt, bis 45 oder 35 Personen und dann legen wir los. Blödsinn, doch, das brauche ich. Das brauche ich. Bloß nicht die Ansicht. Keine Lust mehr zu warten. Yeah, let's start. Welcome to our 5th lecture on distributed information systems. Before we start with the content, a small remark. In the next year, on the 13th of January, we will use a different link to start our session, because we will have at least one visiting school kid. Is kid the right one? School teen who's thinking about joining mobile computing or automotive computing, and therefore we will have an open lecture, and we will use a link which I will then copy into the chat channel, and then you have to use that link to get to the meeting room and to the lecture room. But I will remind you on Tuesday when we first meet again in the new year about that. But as a small remark in the beginning, to wait for the others to join. This can be or will be of interest. Right. What's up Today, we will continue with synchronization, so multi-threading problematics. And then we will continue with how to build Java-based socket clients and stuff like that, and some general remarks regarding middleware and threading in Java. Whereas threading in Java, I think I moved that to the back of the lecture because we will be getting into time trouble anyway. So this has been moved, and as the Java side doesn't need to be multi-threaded, we can live without threading on the Java side. Which brings us to what needs to be conducted today. So let's share a screen, share this screen. Let's share this screen, move that here. And take a look at the exercise. Where did I drop the exercise? I dropped it here. So you should be able to see my screen now and the current exercise. So today's exercise will be about, first of all, those of you who haven't done it yet should try to work on the threading aspect, so 1.2D. As I already said, if possible or if time is sparse, forget about B and C. D is more important, and especially more important it is as it is mandatory. You have to work on the part 1.3a. What's the thing about 1.3? At this or till this point in our exercise, we just did the communication between client and server. So just sending around funny messages and getting some acknowledgements. And now it is time to really do something useful with our client-server communication. As I already stated multiple times, the idea is that the server has some kind of service we want to use. And the client needs to somehow tell the server which part of the service it wants to use and trigger that usage and receive some answers from the server. And in order to do that, we will facilitate a small protocol which helps us tell the server what we want from it, and the server constructing an answer which we will then use on the client side to do something nice. And 1.3a is the exercise part where you should build up a TCP server, the environment server. This is the, I'll give it back to this nice little exercise. So it's the fifth option, the environmental server, which we should use or generate in 1.3a. If that is an IP version 6, IP version 4, I do not care. Multi-threading would be nice, but isn't necessary. That's the reason why the threading part is optional. Nevertheless, we need an environment server to have the fully working example up and running. So this is a mandatory part, and I try to write down the protocol. So the first line or the first row is typical the structure of the protocol, and the second line is an example call. So the client request sets up or sends the command get sensor types, and the server responds with what server types it is supporting. So in this case, light, noise, and air. As you can see, the protocol is based on terminal tags. So the client and the server know that a command has been received when they find this termination symbol. Then they know, okay, the command has been, or one command has been received. And starting from the first byte to the one before the terminal symbol. So the first command we can, or the first question we can ask the server is what sensor types it supports. When we know on the client side which sensor types are supported, which is a semicolon separated list, Then we can ask the server for a very distinctive type of sensor. So we can send the server get sensor, and then we specify which sensor we want to access based on these reply content from the server. And when the server receives such a command, again, terminal symbol marks the end of the command, then it replies with a timestamp, the current time in millis, and then number of values. It can be one value, and it could be multiple values. If there are multiple values available, it's again semicolon separated list, and the two elements that are communicated, the time and the value section, are separated by this or operator symbol. So that's basically what the server is doing when it receives a request. And in the exercise, there will be, on the C++ side, I think we can query the server with we can query 3 different sensor types. And one of these sensor types should reply with multiple values, and the other ones can reply with just one value. So one of these replies or send, if questioned, reply with 3 sensor values or 2 sensor values, and the other ones are just returning 1 sensor value. The values themselves can be randomized integer values, and they're just representing dummy data. If you want, you can, of course, generate some useful data. So what is this? Noise, light. So some negative light values are not really useful. Could orientate yourself on lumen or noise, decibel, air could be okay, carbon dioxide, microparticles, and temperature, for instance. Something like that. It's just dummy data that gets communicated, but it should be randomized. That's important because later on we want to see that something on our dynamic web page is changing, because in the background the server is always changing the values, and we don't need a database in this section. This can be hard-coded, no problem at all. So that are the 2 main queries we will support on the server side: get sensor types and get sensor air, noise, or light, and then some values. Or we can use the shortcut where we can query the server with get all sensors command, and then the system returns automatically with the data that it is providing. So again, timestamp, and the light sensor with its values, the noise sensor with its values, and the air sensor with its 3 values. And again, the terminal symbol as a provision. That needs to be supported, and at this point in time, you can use specific C++ classes. So you can use string classes, vector classes, hash maps, whatever you like. And you should, this should be the environmental server, number 5. And you should test your functionality with a working C++ client, which should be command line based. So you just send this command to the server, and the server replies with some data, and you print out the data. Everything fine and easy, and everything is working. And when we have the environmental server up and running, we start building the communication counterpart, not in C++ anymore, but in Java. And in order to prepare that, we start with building a client-server tuple that rebuilds this echo server we've already constructed in the C++ world, but now on the Java world, which is far easier and should take up less code. So if you never have done that, do the optional warm-up exercise. If you already have experience with Java socket programming, you can, of course, skip that and go right to the mandatory part, where you have, first of all, a Java socket client, command line based, which communicates with the C++ server using the protocol depicted here. So you can send on the Java side these commands and receive from the server side these replies. In 1.2b, the protocol doesn't need to be implemented. It's just an echo server, just playing around. And then you can reuse whatever you did on 1.3b, the client, and just connect to the C++ server, which is just using a different port as you are practicing that on your computer alone. And that should work like a charm. And when this works like a charm, then you build on the client side, on the Java side, you define this interface, which looks exactly like the protocol in the background, or very similar to the protocol in the background. So you provide a Java interface that looks like this. And then you provide a class that implements this interface, presumably your Java client, which you use to test the communication to the C++ server. And when your client implements this interface, then you need to send to the C++ server the appropriate commands when this method is called. So when this method is called, the Java client sends the command get sensor types to the C++ server, receives a string. The Java client receives this string, cuts the string based on the trend symbol, or based on the marking symbol, and delivers a matching string array back to whoever called this method. And in order to test that, I have a slight code fragment, which you should just copy and paste into your main method on the Java side. And as you can see, we use the interface. This will be your class, which implements this interface and which is communicating with the C++ server. And then you use the different methods available, print out the results, and do that as long as the program isn't killed. And when we've achieved that, then we are done with this socket communication and move forward to the more easier and less brutal approach, and use remote method invocation and remote procedure calls to achieve similar results, but with less effort. That is what we want to do in the exercise. So the important part is getting today to 1.3a and get it ready as far as possible, because on Thursday, and I postponed the upload of the exercise to Wednesday evening. On Wednesday, you have to solve this Java client communicating with the C++ server. And making these exercises here should be way easier than the C++ side. But we will see. If you face any problems, contact me, please. Are there any questions regarding the exercise? None, that's nice. If you should have any questions, ask Mr. Plattner or ask me during the exercise. We are happy to sort things out for you if necessary. Right, so having said that, I can close that and I can close that, which brings us back to our lecture. And last time we talked, we stopped, as I think I remember, at concurrency and synchronization. So we were talking about how to do threading by using the create thread method, which is important to tell the system which method should be parallelized. And depending on the system you use, it's either pthread create, because we're using the pthread classes. We have this client communication. Be extra careful with this and symbol here, because this could either mean your system works or it doesn't, or it will definitely not work. Same, of course, on this side here. So extra careful with that one. Yeah, this is the Linux, iOS, CLine side, and the create thread. This one is for the Windows Visual Studio users. And then, yeah, basically we had to define a target method. Careful differences between Linux and Windows regarding the return value. This is important to be reflected, and this one needs to be static. And only this method needs to be static. Don't try to turn your whole program into static. If you want to communicate something that is inside the server and provide it to this client communication method, you have to use or communicate it through the parameter used here. And in order to communicate multiple parameters, use a struct where you can put in everything, anything you like. And if you need specific methods, properties of the server, just put a reference to the server into this struct, which of course could mean that you get the problem of synchronizing the access to these resources, which is something we talk about in a minute or two. But yeah, you decide by structuring your server. The more complex you structure your server, the more side problems you open up. But some of you have already recognized that. So keeping things simple, but not too simple. It's always a very narrow margin where this, how to do this in one way or another. So this is an example how to encapsulate the parameters. Yeah, on the WinSock library, some general aspects regarding the attached and detached threads, because when we have detached threads, we have to wait for the threads to stop and join the main UI thread again, if you want to call it this way, in order to have everything cleaned up. Which of course is work on the programmer's side. And if we have detached threads, then we typically don't have that problem. Aside from that, of course, in C++C, you always have to make sure that that memory that you allocate dynamically gets deallocated again. So otherwise, you're generating memory leaks into your program. So try to clean up as best as possible after yourselves. Nevertheless, this exercise is not about building 100% clean code. It's about communication. So if time is sparse, and I assume time is sparse for many of you, lay that problem aside. But be aware that there is a problem if you mess up with the memory. And use up all the memory. Aside from that, yeah, we had the join method if you have attached threads, and we had the detach method, which can be used to detach a thread. Detaching a thread can be done when you construct it, or so you construct with create thread, spawn a thread, and then you can tell using the thread name, you can detach it, or when you are inside the thread yourself, you can detach yourself. And there must be an example fragment a minute or two later, pthread itself. Yeah, exactly. Detach. So this code fragment can be used when you do it inside the thread method itself or outside the thread method. And this, as some of you already recognized, was if you're keeping an array of thread IDs which are currently in use inside the memory, then of course you have to use an array of some kind. But of course you can also change that and use it completely differently. Cleanup is something like a destructor method which can be called or which will be called when its existence is announced, when the thread gets killed. So this method can be used to clean up some memory when the thread has been left. Quite useful if you do lots of things on the heap. Can be used, doesn't need to be used. Close handle, again, if you have some kind of handle, which of course is a thread, is some kind of active object, a community socket is some kind of active object, database connection is some kind of active object. And always if you have some kind of active object which you need to open, activate, initialize, there's typically a close method nearby. And there is a reason why there is a close method nearby, because you should close after you left. So it's basically like a door in your house when you open the door. And of course, if you leave the house, you close the door again. Otherwise, everything will be wide open, and then bad things happen typically. Wait for single object and wait for multiple object. The equivalence to the pthread join on the Microsoft side. Yeah, and I think that was the part where we left our lecture last time. So coming to something new, before the reason to do a slight introduction into concurrency is the reason because when we have concurrency, typically if bad things can happen. Let's say just bad things can happen. In order to have no bad things happening, we have to know about synchronization. And this again brings in more complexity. So let's again recapture concurrency. So what is concurrency? If in the documentation, if you use some nice books out of the library, you will see that there are different definitions of what concurrency really means. And the one I used is some book from C-Cord. I don't know if that is the best one, but I found the definition quite nice. So if two execution flows, so you have two parts of the execution flow of the program is one command after the another, and now you have two that are seemingly or in reality executed in parallel, then we use this phrase concurrency. They are executing concurrent. And a typical example, the book states the browser receives data, builds up the web page, and the users are still interacting with it. And similar to an Android or iOS program where in the background some data is received from the server while we are playing a game. And this, of course, needs concurrency. There is no way around it. The typical problem if we have concurrency is the so-called race condition. And the race condition, we will have a picture later on that which I used to explain the problem of the race condition, is an unanticipated execution ordering of concurrent execution flows. So in your mindset, you say, okay, this goes in first, does something, the other one goes in next, receives the data, and then does something up based on that data. And now suddenly the execution order has changed. The one starts, gets interrupted because they are sharing the CPU, and the other one is started. That reads the data, manipulates the data, changes based on the data its behavior, and then the other one starts again. But it was stopped after reading the current value, so it uses an old value as its base to calculate something. And of course, this base it uses is already old because due to concurrency, it has changed in the meantime. But the other execution flow doesn't know that. And therefore, the system really gets out of hand. And this getting out of hand results in undesired behavior. So we are working on an outdated state. So, and then of course, our result of the calculation can only be wrong. Or if we are very, very lucky or unlucky, would be real if something useful pops out. And unlucky, why is getting a decent result unlucky? Because this time everything went well, but the next time perhaps it doesn't. And then it's undeterministic errors. And those are the worst because you cannot know what generates them. And this makes debugging extremely hard because you debug, everything is fine. The next time you debug, something bad is happening. Next time you debug, fine, 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 bad, bad, bad. And this is really, so undeterministic behavior is worst case of everything. The other problem that can arise, and this will arise when you try to cope with the problem of the race condition and use synchronization, then you have something that is called a deadlock or a live lock. How can I explain deadlock and live lock the best? The best example is you walk down the floor inside the university. So you walk down the floor in the middle lane, and someone pops up in front of you and also walks down the lane to you, and you both go in the opposite of each other, go facing each other. And then the problem arises, okay, you need to change side in order to pass each other. And a deadlock is you wait for the other to make a decision left or right, and the other one also waits left or right. This is a deadlock. Nothing happens, and you just wait for the other one, and you wait forever. A deadlock. You're dead. You're locked. The live lock on the other side is, okay, the you facing person chooses to go right, and you choose to go left. So you're facing again each other, and the one going left and you going right, facing again. So you toggle the situation, but you're still not moving. And this is basically what a live lock is. And all this together, so when this can happen, we are talking about a race condition. So a race condition is this unanticipated execution order, which really makes your life hell. And what is necessary to have such a race condition? So this is a problem that is known from the beginning of concurrency, which is the beginning of computer science. So the people already realized, okay, in order to have this kind of problem, some conditions need to be present. And in case of the race condition, 3 distinct conditions need to be present. One, of course, is concurrency. So there need to be at least two execution flows concurrently. You need to have a shared object, so something they both want to manipulate. And these race objects must be accessed by both of the concurrent execution flows. Of course, if there's just one entering it, then there is no problem. There is no race condition. But if they both want to access this shared object, problems may arise. And they will arise at some point in time if the third condition holds true. And the third condition says if one of the control flows wants or must or will alter the state of the race object, the shared object here, then bad things can happen. Then we have the probability of a race condition. If they all only read the data, nothing bad can happen. If one of those changes the data, then something bad can happen. And depending on what you're doing, this can be your brake system is shutting down, or you're just receiving the wrong data and in your computer game. And of course, nothing bad happens with that, but you're just annoyed that something is not as you wanted. So these three aspects are necessary to have a race condition. You need to have concurrency, which is typically available in every modern decent program. You need a shared object, so something both concurrency flows want to access. And one of these, or at least one of these, wants to change the state of the system. And then you have a problem. And this is exactly the aspect of the option of the bonus part of the exercise, where you generate a shared object which different threads want to manipulate. And in order to prevent this race condition, or to prevent this race condition, you need to, of course, identify the race window, which is sometimes called, or in other documentation is called, critical section. So this is the part of the code which shouldn't be interrupted. So you know, if I'm reading this data and get interrupted and someone else starts with the processing and changes this data while I'm not active, then I'm using an old state, I'm using wrong data. So you need to define what is shared, what is the shared object that both elements or all the concurrent elements share, and at what point does this change occur. And this change is one of the bad things. If they are all just reading, everything is fine. If one of them changes, then it depends. It can also be a bad sign for the reading part, because I read something, and typically if I read something, I'm using the value to continue with my processing. I change my state inside my program. And so I need to be dead sure that the state is the one that I really want to have, and not something that has been, I read the data, then I'm getting interrupted. The next execution flow starts, changes the data, and then suddenly I have old data, and I'm using old data. And this needs to be managed. And in order to manage this problem, in order to eliminate this race condition, is by making these race windows. These race window is again part of the code that is the problem, mutually exclusive. And making a race window mutually exclusive is done by synchronizing them. So we have synchronization mechanisms which can be used to cope with the problem. Let's take a look at the next slide. So this is the problem again. We have the main UI thread that is executing on the left side, and we have the thread that is concurrently executing on the left side, and this one on the right side. And they both want to use a shared resource. And they both read some data from the shared resources and write something, after doing some calculations with it, write back some new data into the resources. And of course, the execution order of these two makes a difference. So these parts of the code are the race windows. And I have to make sure that if main enters this race window, that the thread cannot enter the race window until the race window on the main UI thread has been left. And from here from this dot to this dot, the main thread needs to have exclusive rights over the resources. And this is done by synchronization mechanisms, or the other way around. The thread begins, as you can see, slightly over the first dot of the main thread. So this one would block the resource, the use of the resource, using a synchronization mechanism. And when the main UI thread tries to access that, this synchronization mechanism actively blocks the main thread, or can actively block the main thread. In our situation, the main thread would be hindered using the resource. It would actively wait. The thread would continue with its processing, comes to the end of the race window, opens up the access to the resource again, and then automatically main is left through the gate and can then work on the resource. And the problem, of course, with the synchronization is, if you do it wrong, you can get into this deadlock lifelock mechanism. And yeah, this needs experience, and therefore, if you have time, play around with it. If you don't have time with it, be aware of this problem, and there will be tons of situations in your future life where you have this concurrency problem, and hopefully you remember then what you heard today. So how to do the synchronization in our system? We can do the synchronization in multiple ways. There are tons of mechanisms, but they are typically all the same. So depending on the system, you have so-called critical section objects, or you have mutex variables. We have semaphores, pipes, named pipes, condition variables, lock variables. So tons of things we can use. Typically, we are using mutexes, and sometimes mutexes are not only for the process itself, but also processes that are parallel to you, managed by the operating system, but just naming conventions. So mutexes, simple critical section guards, are commonly used. We have semaphores, which are slightly different than the simple mutexes, but we see those later on. So these two will be used in our situation. And so this is how it works when you do it with synchronization. At some point in time, you initialize your synchronization mechanism, and then you execute both of these concurrent command flows. And at some point, one of those wants to get to the resource, so it locks the synchronization mechanism, which means the other one that is accessing this gate, the second, in second place, is standing in front of a locked gate, and it waits. If you don't define it otherwise, it waits here actively. So your application flow is blocked. Again, this needs to be coped with, because if you block the main UI thread, then of course your program freezes, which is typically not what you want. So this needs to be executed in a separate thread again, and yeah, you will get the problem. So we lock it, then we are executed, and we can be stopped here in our execution flow, and main can be activated again. It will not, due to this locked gate, it cannot access the resources. So it waits, and the thread is reactivated again, restarts here, goes down, goes to unlock, is continued, is again postponed. Now main can enter the gate, locks it behind itself, and is inside this critical section, and then it continues. At some point, the thread is finished, and as I already said, if you have some kind of active element used in your program that you initialize, open, you have to close it again. So at some point, this synchronization mechanism needs to be disposed again. And this, there's always an open method. When there is an open method, in 95% probability, there will be a close companion nearby. Okay, this brings us to the critical section. So the simple way to put a gate around the race window, the critical section. So how is this done? On the Windows side, it is really called critical section, and you can initialize a critical section, enter, leave. So this is locking the gate. This is opening the gate again. Some additional ones to check if the gate is open or not. If you don't want to, if you may want to make sure that you can enter it, and if you cannot enter it, do something else. And we have the additional ones on the Linux side. Problem with the Linux side is that it is not supported by iOS. On the iOS world, we at least we had the problem last year and the last years is we have to use semaphores, but they are simple. We can use semaphores as well. But for all the others, we have pthread mutex in it. We have the type of the mutex of the critical section guard, and we can initialize that. We can lock it, unlock it, and later on destroy it. And then we can use that. Right, and that's exactly what we will do. These are the critical section aspects of Windows. As I said, we typically initialize or we build a new critical section. Don't need to do that. You don't need to do that on the heap. You can initialize that. Then you enter the critical section, do some critical stuff with a shared resource. And when you've done doing your thing with the shared resource, leave the critical section and later on delete the critical section. Of course, the big problem is, this is what is shown here, when you do something and you're locking the gate and then your program is killed, or better shown here, if the thread dies because you made a programming mistake, then of course the problem is that this door is never unlocked and your program is in a deadlock situation for eternity. So it's really, really, really important that if you have a critical section, a race window, which you synchronize with some kind of mechanism, you have to make dead sure that nothing bad can happen. Or if something bad happens, that you have some kind of exception handling that makes sure that the last thing you do is, if you are leaving this block, that you unlock the gate again. Otherwise, yeah, you're in real big trouble. So this is on the Windows side, and the equivalent on the Linux side. So you can initialize a mutex with attributes, but we don't use attributes. So you build up a mutex type, which can be static, which doesn't need to be static as far as I remember. Then you have a mutex, initialize it, you lock it, you unlock it, and later on you destroy it. Which brings us to the next synchronization mechanism. So these are just gates, singular gates, which we talked about. And the next thing we talk about are the so-called semaphores, which are also gates, but slightly different gates. And looking at our clock, I say we make a 5-minute break. So at 10:35, we will continue and talk about the problem or the feature a semaphore offers us. Okay, so a small break. And after that, we talk about semaphores. Right, so I will mute myself and then we will continue in 5 minutes, 10:35. Okay, 10:35. Let's continue. As I said, these critical section or mutexes are singular gates, so only one can pass an open gate, and if the gate has been passed and locked, no other element can enter. Semaphores are working similar, but they can make, depending on which system you're working, they make sure that n threads or n parallelized concurrent execution flows can enter a race window at the same time. And depending on the system you're using, you can define the maximum number or you have to check the maximum number. The thing about the semaphores is that if you're using a semaphore, you are using a counter internally. The semaphore is a counter. And the thing about the semaphore is the semaphore can never be negative. So if the semaphore is at 0 and one tries to enter the gate of a set that is guarded by a semaphore, the semaphore tries to decrement the counter. And when the counter is already 0, it cannot decrement the counter because then it would be negative and this is forbidden. So the semaphore blocks and the execution flow is blocked with it. And only when the semaphore is left by something that is inside the guarded area of the semaphore and increases the internal counter of the semaphore again, then the waiting one can enter the area of the semaphore and decreasing the counter at the same time. So this is basically the idea of a semaphore. You can have an area where you can manipulate the amount of concurrent execution flows that is working in this system. And for the iOS people, of course, if you define the size of the semaphore to 1, then of course this also works perfectly as a mutex variable. And then you can work with that. In order to build a semaphore on the Windows world, we just use a general handle and then use the create semaphore and use wait for single object and release semaphore and delete critical section. So this is quite confusing naming convention because it reuses stuff. On the Linux world, we have the semaphore type and semaphore init and semaphore open. And we have wait and we have post and we have destroy. It's slightly more sorted. On the iOS side, we have another problem. There are named semaphore and general unnamed semaphores. And the iOS world only supports named semaphores, which are, and when they are named, they can be used over process boundaries, which of course makes it more complicated because semaphores that are usable over process boundaries typically are held alive even if the process is closed by the operating system. So when you're using semaphores on the iOS world, you have to make dead sure that you at some point call semaphore destroy. Otherwise, you are leaving semaphores actively inside your system and they only get destroyed after you restart your computer. So extra careful on the iOS world. Of course, nothing bad happens if you have a dozen or two semaphores on your laptop, because memory is not really a problem on that machines anymore. But in the old times, that was still a thing. So this is how to use it on the Windows world. Yeah, lots of explanation. Create semaphore, wait for an infinite amount of time, do something critical, and release semaphore. And depending on the system you have, there are different ways. So there is a start counter and a max counter. So this semaphore cannot exceed the max counter of 1. And this, of course, can be nicely used, and it works problemless. Release semaphore. On the Linux world, we have the semaphore init method and later on the semaphore open method. which needs to be used for the named semaphores. So this is the initialization method for the unnamed semaphores, which cannot be used by the iOS fraction. But nevertheless, they are quite similar. So you need a semaphore type. You define if it is shared over process boundaries. In our case, we don't want that. And you can set the initial value of the semaphore. And next slide, we have the open method, where you give the semaphore a global name. Then you get some construction flags and some mode mechanisms. And again, the initial setting of the semaphore. And yeah, the remarks I already did. We can use named semaphores in multiple processes as they stay alive over the process that was used to initialize it, open it up, need to be unlinked and destroyed. And then basically semaphores with the size of one work like mutexes. So you can use it in this way if you want to. So this is for the Linux world, the top one, and the bottom one is how to use it on the iOS world. So you need to give it a name. If you want to be on the safe side, you can try to unlink or destroy the semaphore that might be available on your already on your system, and then you open up a new version of it. And then you have some creates and exclusion options and some octanal definition which processes can manipulate the semaphore. I try to write it down here. So that's basically the idea, what is used here, and the starting size of the semaphore. Exactly, and then we have the semaphore wait, and so entering the critical section, and semaphore post, leaving the critical section, and semaphore destroy, destroying the semaphore after its use case. Careful, destroy, yeah, for the unnamed world. And this brings us to the end of this lecture part, Introduction into Concurrency and Synchronization Mechanisms. This, of course, is a very low-level approach to the synchronization, and all modern languages like C#, Java, Kotlin, and stuff like that, they all have synchronization mechanisms. Sometimes they are called slightly different, sometimes they are used by integrating annotations, but they all have these synchronization mechanisms, because when you integrate concurrency, you open up and the three conditions hold, you open up a race window, and then things get messy. Even if they work 100 times and you tested it, it works nicely, there will be one time where it doesn't work. And then you need to think about synchronization. It's dead important. And the problem is you need to do it, and you open up a box of lots of problems with that one. And this makes our life even more complicated than it is already. But we can't help it. That's just the way it is. So that's the good thing about the exercises in our lectures. You can do a lot of practice, and nothing bad can happen when you do some not perfect solutions, because it's just an exercise. So all you can get is me saying this was not the best solution. But nevertheless, you will pass this lecture. This brings us to our next slide package, slide package 4, and I updated it this morning. So if you have downloaded the slides before this lecture, you might want to update it again, because I changed it in the last hour, because I realized I changed it last year and last semester, and therefore I presumably have forgotten to update the PDF. as Mr. Steiner said last week, we had a discrepancy between my slide PowerPoints and the PDFs on the Moodle platform. This should not be a problem today. So what do we want to talk about? First of all, we need a socket client on the Java world. So first thing we talk about is Java sockets. And I need to change that. In the headline, there was threading also available, but I moved the threading part to the Anhang. What's Anhang in English? Don't know. So the stuff that is at the back of the lecture. So you just look at the last pages of this lecture slides, and then you will find some decent information about how to do multi-threading in Java using the runnable or callable interfaces. And then if you wanted to, you could integrate concurrency even on the Java world. But in our exercise, we don't need concurrency on the Java side. We can stick with one control flow, and this will be perfectly okay. On the C++ side, it would be nice if you integrate concurrency, at least try to integrate concurrency, because you need all the practice you can get on that topic. So sockets on the Java world, in general, we already know that sockets are endpoints in a two-way communication link between two programs running on a network, communicating over a network. They are part of the Java.NET package, and they've been there from the beginning of Java, because doing communication is one of the basics we would typically want to do if you build some complex programs. It's basically a connection between a client and a server. And we have two separate classes, one for the client and one for the server. So the socket class is used for the client part, and the server socket is used for the server part. Whereas the server socket accept method pops out a socket instance, which we then can use to establish communication between client and server. So it's basically the same as in the C++ world. It's the same in all programming language. If you know the concept, server socket needs to be bound to an address, waits in the accept. The client builds a socket, uses the connect method to connect to an accept waiting server socket. Server socket pops out the communication part, and then client and server can communicate, and the server, if multi-threading would be supported, wait for the next client to reach it. It's basically always the same. Therefore, it's nice. If you know it, if you manage to do it on this very low level C++ Berkeley socket library, you will manage it with every other modern programming language with no problems at all, because they are way nicer to be used. Classes containing everything you need, not needing to do everything on your own. Very, very, very nice. So, and of course, when you got your when you're out of the accept method, you run into this queue where you start communicating with the client by doing something. So what are the interesting parts of the server socket? We have a bind method on the server socket, but of course we also have multiple constructors, and some of the constructors already incorporate the knowledge to the address that needs to be bound to. So the bind method is optional depending on which server socket constructor you're choosing. The accept method is, of course, mandatory. You wait on the server side for a client to connect to you, and then if this is conducted successfully, the socket pops out, and then you use this socket reference to communicate with the client. And of course, when the communication with the client is finished, you close the socket again. So the close is available for socket and for server socket as well. And then you can work with that. Socket address is an abstract class that can be used or is used to define which kind of socket you want to construct. And we will use an IP socket address. And you can use this kind of constructor or at least half a dozen different other ways to construct this. The socket on the client side is, and later on for the communication mechanism, which also provides lots of methods, which are the important ones. The important ones is, of course, connecting. We want to connect to a server, which we target with a specific address. So which server do we want to target? So we need the IP address and the port number, of course. And then we can connect to a waiting inside the accept method server. And when this connection is established, then we can use the socket references to communicate between client and server. And on this, in the Java world, this is not done directly. So the socket doesn't provide a read and write method. What it does provide is a get input stream, get output stream method. The input stream is used to receive data. So I'm getting input. The input stream is for I'm getting input. And the output stream is used for I want to put some data out. So you can use that Eselsbrücke donkey bridge. I don't know if that's a brutal translation, German to English, but this should help you remember that. Input stream is I'm getting input. You have to look at this streams from an ego perspective. I'm getting input, I'm generating output. Because typically I also sometimes get confused, okay, what was input? Do I provide input for someone else or do I receive some input? So you have to look at this from the socket perspective, from an ego perspective, and then you can choose that quite wisely. So getting some input means the input method provides lots of read method. And not only those that I've depicted here. So you can read one byte after another from the input stream until no data is available anymore. Or you can just grab a chunk of data and see what happens. And of course, it also can be closed. On the output stream side, we can write data into a socket or into the output stream, which then sends the data to the socket, and the socket sends the data to your communication partner. So you can write a single byte into the stream, or you can write a block of bytes into the stream. If you write a single byte into the stream, don't be afraid you're not sending once, most of the times you're not sending one singular byte over the network. You're just shoving one singular byte into the queue of the socket. The socket, as I already told you, is smart enough to know, okay, let's wait if there is more data available. So you can write 1,000, 5,000 bytes into the stream, into the stream until the socket decides, okay, and now we send these 5,000 bytes over the network. Or if you call flush after every byte you write into the stream, flush is like the toilet flush. You send everything through the tube to your communication partner. So if you want to define now send the data, you can pull the flush and then everything is flushed out of the stream and into the network. And of course you can close the stream again. If you have opened it up, you need to close it in the reverse order, of course. So this is an example for a server side of socket communication. So what do we have? We have a server socket that already has a port defined. So this one is running on localhost at the port 1, 2, 3, 4, 5, 12,345. And then this things goes into the accept method, waits for a client to connect. If a client has connected, sock is the reference to the TCP communication that is able to communicate with the client. Sock is used to extract input and output stream. And as we are on the server side, we of course wait for input. So we first of all read data. And in this case, we read data until no data is available anymore. And we are reading just one singular byte. Of course, this is not the most optimized way to do it, but it's working, and it can work for you as well. The data, what we can also see here is either the reading, the input stream is corrupted at some point, then it returns -1, or I receive some kind of terminal symbol. In this case, it's a line feed, \n. And if I receive the \n, I'm breaking out of this loop, and then I could send some data. I could interpret whatever I've appended in this string buffer line, and then send a reply. And the sending reply part is missing in this example because you can do something on or find an own solution to that, of course. The client side, again, something similar. This time we are defining the IP address. So we are targeting localhost, and again, this port. We define, I've forgotten the connect method. There is a typo in here, and no one has ever told me that. Or is this one executing automatically? Nah, I think I forgot the connect method. So there's a huge typo in here, and no student in the last decade has ever mentioned it to me. This is interesting.
Hi, this is Michael. The socket constructor already connects to the.
Okay. So it's not a mistake. So it does that.
Because I was one of the students in the last decades that didn't mention this problem because there is no problem.
Okay, perfect. Thank you, Michael. So again, and this is one of the reasons why we are doing this C++ thing, because when you use these modern programming languages, multiple things are done automatically in the background, and you have no clue what it is doing. And of course, you don't know that it is necessary to connect to the server, because if you are just know the socket version of the Java world, you wouldn't realize that because you saw the example and this works, and therefore you don't know about that. And this is always a problem because some other programming languages, for instance, don't support that in this way, and therefore it automatically brings you to how is this working. Right, so we have the socket, we get the input and output stream. If it connects in the background automatically and it works like a charm, then we don't have a problem, and sock will definitely have something valuable available for us. And then, of course, we can send the data. If you want to know what's the typical, or what's, let's say 20% of you will make an error in this exercise with the client server communication on the Java side. And the typical error is you will check the internet, you will find lots of examples how to solve the client server socket communication using Java. And some of them will use readers. And you will use the read line method on the server side. So a typical error, and 5 or 10%, 5 people of you will definitely have this problem, that you're not using this kind of extraction of the input, but you're using an input stream reader, and you will use the method readLine. So you want to extract one complete line that this client sends you. And you program that, you start it, and nothing will happen. On the client side, you send data, and the server will not receive it. And the reason why the server will not receive it is that you're not sending a line. readLine only is left when the line feed symbol is communicated. So the error you're doing is you're sending data, but you're not sending the line feed symbol. And therefore readLine is not, the line has not yet finished, and therefore it will block. And at least 5 people of you will do the error. Will be interesting if you're still doing it while I mentioned it, because you're not listening. But we will see, and it will make me smile. Definitely make me smile, and Michael presumably also will smile. So this brings us to a new slide. So what's the current knowledge status? So this is what I wanted to explain you with the introduction into the exercise. So we, at this point, had a simple client-server communication. We had a simple exchange of messages, hello world, foo, bar, and we had some kind of real communication. No real communication. We had some kind of communication, but the reason, or the 1.3 exercise, is about doing some useful communication. No echo. We want to trigger some services, methods on the server side and get some real results. And that's the reason why we integrated this this protocol in the background. Of course, it's a very simple protocol, but of course we have only decent amount of time in our exercise, and we at some point have to finish. And of course, in our situation, we have one client communicating with one server. And of course, this is a very, very simple point of view. And we all know that in the real world, a distributed system is made up of multiple servers and thousands of clients, and not only one server, but web servers, application servers, database servers, calculation servers, the cloud containing multiple virtual servers, and all these aspects. And of course, they are not all running on the same language, and they're using different languages, different machines, different libraries, and this makes our life more and more complicated. So in reality, it looks even more complicated than this, but you can see there are multiple components used and depicted here. And what I already did was, I, as part of my knowledge, my experience, I always try to do things in an orderly fashion. I dislike chaos. Of course, I could have made a map, like a mind map, like a graph that contains multiple aspects in any directions. But as a computer scientist, I always like order, because order helps us to keep the complexity at bay. And of course, this is a typical thing that we do in computer science, and of course in different other sciences as well, but we are Fachidioten, so therefore we are just using computer science as an example. And one thing, and this is a small excerpt or a small sidestep in this lecture, in order to keep this order and fight the chaos, computer science came up with the idea of software patterns. And software patterns are providing solutions for reoccurring design problems when you develop an application, a system. So we had these problems in the early stages of computer science that many projects tended to go way over time or completely did not go out well. And they, of course, thought multiple of them were scientists, and they thought, what did go wrong? Why did it go wrong? What could have been made better? And software patterns were not only envisioned then, but they got a real hype at that point, because they showed us, if you have a specific problem that looks slightly like this, there are different patterns to cope with this. And these patterns showed successful solutions. So if you work on this problem in this manner, your chances of succeeding with your project or with this part of the project are higher as if you do it totally chaotic. So this was one of the birthdays of the software patterns. And when we use software patterns, we typically have to somehow write them down. And in order to write them down, of course, we are structured people. We always want to use the same structure in order to make them comparable and exchangeable and identifiable. And this, of course, is something that was also used on the software pattern side. And on the software pattern side, typically you describe the context. So in what kind of situation does this pattern work or can be used? Of course, it's not 100% clear. There are definitely some situations, contexts where this pattern also could be useful. That depends, or this totally is due to your experience. Later on, you see, okay, this could be useful here and this could be useful there. And of course, the problem stating, what is the problem inside the situation, and how does this pattern solve this problem? The problem with this problem statement is that we typically have contradictory parameters. So you want to have something fast, but you want to have something safe. And typically you cannot work on both goals or achieve both goals with the same amount. And therefore you always have to be careful with software patterns. There are always people who are very textbook affine, textbook loving. So when it is written, it needs to be done exactly how it is written. But this doesn't work in computer science. The problems are so diverse, so always changing, so huge, that these software patterns are more like Lego building bricks or some Knetmasse, some stuff you can manipulate and adapt to the problem at hand. So don't try to be too on the book statement on software patterns. They are just cooking recipes that give you an impression, okay, this could be done this way. If I change it slightly in this corner and this corner, it will match perfectly. Sometimes you can use the textbook version, but most of the times you have to slightly adapt it. But that's okay for software patterns. And of course, on the software pattern side, you don't only state the context and the problem, of course, you also state the solution. And typically you state the solution by presenting the structure of the system. So what building blocks do you need, and how do these building blocks work together to solve the problem? And then you have to decide, okay, do we need all the building blocks, or can we simplify something, or can we integrate some more complexity? And then you can work on that. Of course, when you say software patterns are used all over computer science, this makes the target space huge. So tons of ways to define patterns. And something computer scientists and all the other scientists are always doing, if the set is too huge, they try to split it up into categories. divide and conquer all over the place. And on the pattern side, we have this splitting up into categories done in different ways, depending on which book books you're reading. Nevertheless, there are 4 categories defined that most of us agree upon. Okay, these are good categories, let's use them. And those are, for instance, the architecture patterns, taking a look at the software system from a huge height and saying, okay, this is data persistence, this is user interface, this is so a rather coarse view on the problem. Then we have the design patterns that go slightly deeper, that are really, okay, if you want to do this aspect, if you want to persist the data, perhaps persisting the data using this pattern is more fruitful, or you are going to be more flexible. And so it's deeper down into the real code. Sometimes you have real classes, and so a structural aspect of a design pattern represents a real class, whereas in the architectural pattern, typically a structural element of an architectural pattern can, of course, also target a singular class, but typically targets a group of classes representing the model of the system, representing the controller of the system, representing the view of the system, stuff like that. And we have the idioms, and the idioms are aspects that are more or less on the programming level perspective. And good example, for instance, are smart pointers. So we already know that allocating data on the heap in C++ brings us some problems. And then someone said, hey, let's make smart pointers, and they clean up after themselves. And others said, okay, let's call it garbage collection. And this is what idioms is about. And also something that arose due to the software crisis in the last century were the so-called anti-pattern. And so the other 3 are best practice examples, and the anti-patterns are the worst practice examples. So they described typical errors in different levels of software projects, from administration, programming, keeping up the backend, or managing all the software examples, where things have gone really bad. And they describe what made the project turn bad. And they explain how to, if you realize, okay, I'm in a project and this is a typical anti-pattern and we definitely need to get out of here, it states mechanisms that help you get out of this spiral into oblivion. And if you have a decent team that you can really use and be critical to yourselves, then you can state, okay, this is a typical anti-pattern. We need to change something. We need to do this and that, or we could do this and that, and in order to get out of this spiral into the project not going to finish on time or at all. Another aspect of the software patterns is depending on what book or what researchers you're following, they tend to have different categories. For instance, the design patterns are split up by the Gang of 4, Gamma and some friends, on creational, structural, and behavioral patterns. And Bushman and some friends said, oh, now we'd have a different other structure, and they came up with a different other structure of the design patterns. And there are other books that come up with totally other different naming convention. This, of course, brings the problem that Bushman defines a pattern that is also available in the structural patterns of the Gang of 4, and they have different names, but they aim at the same thing. So don't wonder if you use 2 different names for the same patterns. You are talking about the same thing. They just have 2 different names. That's always the problem. At least the concepts are still the same, and this is nice. This brings us to the architectural patterns, and again, I chose Bushman to come up with the categories they chose, and they have funny named categories from MUD to structure, Blackboard layers, distributed systems, so client server, broker, service-oriented architectures, peer-to-peer, and so on. So these are the architectural pattern categories which you could stumble upon. Of course, we are just interested in this one here, layers, the ISO-OSI layered architecture. So layers is a design, not a design pattern, a software pattern for architectures, or client-server communication, a design, an architectural pattern for to solve this kind of problems. Model view controller. And we will be, during our exercises, not only today, but also over the next years, we will find tons of these patterns that you stumble upon, and the colleagues and I will tease you with them. And this is, the good thing is, these concepts, they stay forever. The programming languages you use to implement them, they change over time, decade or two, and then new programming language. But the structure of the how to do things, they are stable, and this, of course, is nice. I just skip, as I'm currently looking at the time, we are already at the end of the lecture. So we just do a small slideshow over the next slides, because we just need to take a look at them. So different client server pattern. And as I already said, you have to use these patterns in a textbook manner. Don't be too consequent on that. So these are also client server patterns from a specific perspective. But of course, they can also be different other patterns. And something we will work with later on is the broker pattern. So when we leave this brutal, we do everything on our own and use middleware technology, then the broker pattern will appear. Because in order to communicate between client and server, the broker is used to establish the communication, because the client doesn't know the server. The client only knows a broker, and then queries the broker. Hey, I need someone who can do this kind of job. And the broker says, oh, I have this buddy here, and he will tell you how to do this. And then the broker is used. Sometimes the communication is done over the broker. Sometimes the broker just makes sure both of them know each other, like speed dating, and then they communicate. And broker definitions or broker patterns can be diverse, like everything else in computer science and the world itself. So we can have a forwarding broker, can have a trader, we can have a balancer, and they have similar structures like this. Sometimes the broker is directly involved, sometimes it's just a thing that initiates communication. But there's always a server, there's a broker, and multiple clients or multiple servers, multiple brokers. And this is how patterns are used. You use them to somehow structure the chaos, make it more flexible, more manageable for you. And with those words, I finish the lecture. And on Wednesday, when we come back together, we will start doing some general introduction into middleware. And when we finish with that, we come to the remote method invocation mechanism, and then we can do the communication simpler than we did it today, or did it with C++. Okay, that's enough for today. So closing remarks. We continue as always. I close down the channel and open up a group channel. Keep in mind, cameras are mandatory in exercises, so turn up your cameras. And then I see most of you in the group's channels. And for automotive computing, have a nice one with Michael. See you later. Bye.